Imagine sending a message to your bank, your account details, maybe your PIN, across the internet. What's stopping a hacker from reading it on the way? That invisible shield protecting your data is encryption, and one of the most powerful shields we use today is AES, the Advanced Encryption Standard. In today's short session, we'll unpack how AES works and why it's considered one of the most secure algorithms protecting everything from online banking to WhatsApp messages. By the end of this session, you will be able to explain the main idea behind symmetric encryption and AES. You will also describe how AES transforms plain text into ciphertext using substitution and permutation, and recognize real-world applications of AES in everyday technology. Let's start with a bit of history. Before AES, we had DS, the Data Encryption Standard, introduced back in 1977. It used a 56-bit key, which was strong enough in the 1970s, but with today's computing power, it can be cracked in just hours through brute force attacks. Researchers even demonstrated this in the late 1990s, proving that DS could no longer guarantee secure communication. A temporary fix called triple DS or 3DS was introduced. It basically applied DS 3 times with longer keys. It was more secure but very slow, especially for systems processing large amounts of data. So, by the end of the 1990s, it was clear a new encryption standard was needed, one that was both stronger and faster. To find this replacement, the U.S. National Institute of Standards and Technology launched a global competition between 1997 and 2000. The goal was to identify a new advanced encryption standard, or AES, with very specific requirements. It had to be a symmetric block cipher, supporting 128-bit data blocks and 128, 192, or 256-bit keys for flexible security levels, and it had to be faster and stronger than triple DS. In total, 21 algorithms were submitted from around the world. After multiple rounds of testing and analysis, 15 were shortlisted. Finally, an algorithm called Original, developed by 2 Belgian cryptographers, was selected in 2000. It was officially adopted as the AES standard in 2001. Now that we understand why AES was introduced, let's look at how it actually works, what makes it secure and efficient. AES was designed by 2 Belgian cryptographers, Ridgeman and Damon, and that's why it's also known as the Original cipher. Unlike DS, AES uses an iterative structure, repeatedly applying a series of transformations on the entire data block in each round. Here's the big picture. On the left, we have encryption, and on the right, decryption. Data enters as plain text, and after multiple transformation rounds, it comes out as ciphertext. Each of these steps makes the data more and more scrambled and secure, and the process is reversed during decryption. AES works on 128-bit blocks of data and can use key sizes of 128, 192, or 256 bits, depending on the security level needed. The key is first expanded into a series of round keys. Think of these as variations of the original key, one for each round. AES then applies 10, 12, or 14 rounds depending on the key length. In every round, main transformations take place. Before we go into how AES encrypts data, let's first see how the data itself is represented inside the algorithm. AES works on blocks of 128 bits, equivalent to 16 bytes. These 16 bytes are arranged into a 4x4 grid, which we call the state matrix. You can think of this matrix as the workspace where all the AES transformations happen. Each round of AES is performed on this state. This structure is what makes AES efficient, especially for hardware and parallel processing, since all 16 bytes can be processed simultaneously. Now, let's talk about how the encryption key is represented. AES uses a 128-bit key by default, also arranged as a 4x4 matrix of bytes. From this key matrix, AES generates additional keys for each round through a process called the key schedule. This expands the key into 44 words, one for every round of encryption and decryption. Each round has a slightly different key, adding another layer of complexity. So we now have 2 matrices, one for the data, one for the key ready for the AES rounds to begin. Next, we'll see what actually happens inside those rounds. Each AES round performs 4 operations on the state matrix, subbytes, replaces each byte with another using an S-box lookup table, shift rows, rotates rows to spread data, mix columns, mixes bytes in each column for extra diffusion, add round key, combines the data with the round key using XOR. These 4 steps together confuse and diffuse the data, making it practically impossible to reverse without the key. These 4 steps together confuse and diffuse the data, making it practically impossible to reverse without the key. Let's focus on the first step, subbytes. Each byte in our 4x4 state matrix is replaced using an S-box, which is basically a substitution table. The S-box is carefully designed using algebra over finite fields so that every possible byte maps to a unique new value, providing nonlinearity. This is what prevents attackers from spotting patterns. Technically, we take the left 4 bits of a byte to select the row and the right 4 bits to select the column, and the S-box entry gives the new substituted value. Here's an example using a 4x4 state matrix. We'll substitute each byte one by one using the S-box. Let's start with the first byte, E. In hexadecimal, E is the row and A is the column. When we look up row E and column A in the S-box, we get 87. So EA becomes 87 in the new matrix. We repeat this for all 16 bytes. Each one is substituted independently, and we end up with a completely transformed matrix. Notice how the numbers look totally unrelated to the original. This is what we call confusion, a key property of good encryption. After subbytes, we move to shift rows. This step cyclically shifts the rows of the state matrix to spread data across positions. This ensures that each byte's influence is spread across different columns, enhancing diffusion. For decryption, the inverse operation, INV shift rows, reverses this process. After subbytes and shift rows, we reach mixed columns, one of the most mathematically elegant parts of AES. AES treats each column of the state matrix as a 4-term polynomial and multiplies it by a fixed matrix using finite field arithmetic. What's important is that this step mixes the 4 bytes within every column, so each output byte now depends on all 4 input bytes of that column. This process adds what we call diffusion, spreading small changes in plain text across many bits of ciphertext. In this step, the block is multiplied with a fixed matrix. The multiplication is field multiplication in Galois field. The final step of every round is add round key. Here, the state matrix is combined with a round key using bitwise XOR. This step directly injects the secret key into the data. Even if an attacker knew every other transformation, without this key they can't reverse the process. In this step, each byte is XORed with corresponding element of keys matrix. Putting it all together, here's a full AES round in action. The round starts with the state matrix at the top. Each byte first passes through the subbytes boxes, then the rows are shifted, columns mixed, and finally the add round key step merges the key material. AES repeats these rounds 10, 12, or 14 times, depending on the key length. The repetition, combined with the nonlinear and mixing steps, is what makes AES extremely hard to break. Let's end with why AES is still trusted today. AES was designed after DES, and this gave researchers and cryptographers a valuable advantage. By the time AES was created, most of the weaknesses and attack techniques used against DES were already well known. This allowed the designers of AES to build a stronger algorithm that avoids the vulnerabilities seen in DES. Brute force attack. A brute force attack means trying every possible key until the correct one is found. DES uses a 56-bit key, which is extremely small by today's standards. A modern computer can break DES in hours or even minutes, using brute force. AES uses much larger keys, 128, 192, or 256 bits. A 128-bit key alone has 3.4 times 10 superscript 3 possible combinations, far beyond the reach of any current or foreseeable computing power. Therefore, AES is vastly more secure than DES against brute force attacks. Differential and linear cryptanalysis. These are advanced mathematical attacks that analyze how changes in the input affect the output. DES is vulnerable to both differential and linear cryptanalysis, which was one of the key reasons a replacement was needed. AES was designed specifically to resist these attacks, and so far, no successful differential attacks on AES, no successful linear attacks on AES, even when researchers attempted to apply these methods. The required time and resources were far beyond practical feasibility. Let's end with why AES is still trusted today. It resists both linear and differential cryptanalysis, the main methods used against older ciphers. Its key space, from 2 to the power of 128 to 2 to the power of 256 possibilities, makes brute force attacks computationally impossible. That's why AES is everywhere. It protects our VPNs, HTTPS connections, Wi-Fi traffic, and mobile data. AES is recommended or required by NIST NSA, even for top-secret data using AES 256. ISO virtually all security protocols, TLS, IPsec, WPA3 SSH. This makes AES the default global encryption standard. AES is still trusted today because it is mathematically strong, resistant to all practical attacks, uses large key sizes that make brute force impossible, has been heavily analyzed by the global cryptographic community for more than 2 decades, is highly efficient on modern hardware, and remains secure even against projected quantum threats. That's why it continues to be the worldwide standard for encryption. Before we finish, I want to leave you with one key thought. Understanding AES isn't just about memorizing steps or algorithms. It's about grasping the principles that secure almost everything we do online, from your banking app to your university Wi-Fi and cloud storage. AES shows how mathematics and logic can protect privacy, empower digital trust, and keep our data safe even in a world of constant cyber threats. For computer scientists and cybersecurity professionals like you, knowing how AES works builds the foundation for designing the next generation of encryption systems. So, by learning AES, you're not only studying a standard, you're learning how to think like a defender.